5 minutes dedicated to questions. Please welcome Brandon.
Welcome. Congratulations for slugging it out and making it all the way to the very last talk slot at PyCon. Let's get started. Imagine, if you will, a computer with 1,000 bytes of accessible RAM, numbered 0 through 999, each storing a byte. We can split this memory into pages by grouping together addresses that share a common prefix. If, for example, we want a page size of 100 bytes, so our 1,000 bytes of main memory are 10 pages, then page 3 would include all of the addresses that begin with the number 3, 300 through 399. Now, what is a page table? It sits in between the part of the CPU that runs your code and the RAM on your machine, and it rewrites the leading digits of every processor memory access before the RAM chip gets to see it. Here's an example. The addresses that your process asks for are called virtual, and the actual addresses delivered to RAM are called physical. So this example page table, remember, only looks at the leading digits. Your process attempts to read byte 821. The RAM chip actually sees a request for 6321. Process tries to read byte 190. Instead, the RAM chip would see a request for 3690. A write to byte 522 would be mapped into a write to real byte 6022. And for pages that don't have an allocation at all, an event is generated called a page fault, which pauses your program, returns control to the operating system, and as we will see, the OS then has several options about how to respond. So what kinds of things get stored in the bytes of these memory pages? Well, everything your program needs. The executable code itself, the stack of function calls that are currently underway, the heap with all of your data structures, lists, and dictionaries. These resources, they tend to load gradually as your program runs. Imagine running your editor, which I will not name to avoid obvious religious wars. You say, "Run my editor," and the OS loads it into memory along with any libraries that it might require, taking up a few pages of memory. The editor's main function now gets kicked off and starts calling other functions, so the OS will automatically start to allocate stack pages as that call graph grows. That tends to start at the top of memory and work down as more pages are allocated. Notice the fairly random numbers. They can be pulled from anywhere in RAM that there are free pages because the association is a completely free one. Now, your editor might then, as it starts up, need space for data structures, lists, dictionaries, buffers. It says, "I need more memory." The OS says, "Okay, have some." And you get another growing memory area called the heap, which instead of holding variables that go away when a function call returns, it holds persistent data structures. For those of you new to Python, things like lists and dictionaries. So, what are the benefits of this entire level of indirection that has to be implemented in hardware and invoked every time your process hits main memory? Well, first, security. If the OS is careful and only maps into your memory area your own pages, then you won't be able to see secure data in other processes. You won't be able to see any secret operating system memory containing sensitive information if it doesn't map its own pages into your memory area. And before the OS gives you pages that have been previously used, it wipes them with zeros so that you cannot learn passwords or other data that were there. And obviously, this provides stability. You can't very much corrupt another process's memory or the operating system and cause a crash if you are not permitted to write to its blocks, because they're simply not even visible. They don't even exist to you because they're not in your page table. Now, let's add another dimension of complexity to this picture, the idea of protection. Real page tables include separate read and write bits. In general, the rule is this, that you can write to your own stack and heap as much as you want to, putting new data there, but you're only allowed to read executables in library. So the example app we were looking at would have write bits set on the stack and heap, but only let you read from the editor binary and the libraries that it used. If you illegally read or write, then the OS, again, get signaled, but this time, instead of responding to your page fault by giving you more free memory, the OS will stop you dead with what's called a segmentation fault, which basically means a page fault that made the OS angry. So here, a read from 331, per the rules we saw earlier, generates a segmentation fault because there's no page there. But we've now also learned that you can't write to certain addresses, even if they're mapped, if they're marked read-only. Now, read-only pages, this invention, gives the operating system a new superpower: sharing. Read-only binaries and libraries, when those pages are protected, that means the OS can reuse those pages in everyone's page map and securely share those binaries among several processes. Here are two different processes doing two different things that have different pages allocated in different orders for their heap, stacks, and binaries. But if you look, it's the exact same physical page that's providing libc and another separate page providing libjson, which means those things don't have to use up RAM by being stored twice. Physical RAM page 36 can be reused for every process on the system that needs libc. Similarly for RAM page 39 and libjson, because if you can't write to it, then it looks like it's your own personal copy. It never gets overwritten or changes. This means, by the way, that the total memory consumed by process A and process B together is very rarely the actual sum A's memory use plus B's memory use. So how can you tell how much memory an additional worker thread or process will consume on one of your servers if the OS is letting them share some RAM behind your back? The rule is that you have to just stop looking at the quantity of memory they use and looking for a single number, and you have to start looking as the delta. You have to run 10 processes, 20 processes, 30 processes, and see how much additional RAM disappears from your system pool of memory as you keep increasing the number of workers running. And how can you measure it? Really only by doing actual load and resource tests, because watch this. The story is going to get even cooler and more complicated, and hopefully by the end of the talk you'll be convinced that actual testing and measurement is the only way you're really going to know how much each web worker thread is going to take up. Now, immediately we hit a problem with this idea of sharing binary code, which is Python. Because where in this virtual memory image that your process runs in does your Python code live? Python, like any other process, it starts running with the Python binary and any libraries it uses shareable and only its own stack needing to be writable. But then it runs read on the foo.py file you've asked it to run, creating a writable, unshareable data page on the heap. It will then compile it to what's called a code object, which is another data structure, which is also just a normal unshareable page. And then finally it invokes the code object and the foo.py program starts up, and only that top page, page 7, is actually holding the data peculiar to this run of foo.py. So the heap winds up with in Python as a mix of really unique data, page 7, together with code that's actually going to be shared among every copy of foo.py running. If Python 2.7 is asked to run foo.py lots of times, it's going to generate the same code object. But the OS has no way to know that. It doesn't know that all of your Python processes are rebuilding the same object code every time, and so that memory can't be shared. To the OS, pages that just get written in the middle of the process running look like heap and don't get shared. Now, why don't we come up with some really, really fancy way to try to make that happen, where we could load in Python code in what looked like a normal system library and share it? Why not make them read-only? At the moment, the big problem, as we'll see more about this later, is reference counts. Standard C Python does not support read-only code objects because as you use them, it constantly fiddles with something called their reference count, which is how it remembers when to deallocate old objects. What does this code do when you call function f with the argument 5? it looks up f in the current scope and the enclosing scopes, it gets back a code object, increments its reference count, calls it with the 5 argument, and then when all is done, decrements the reference count. Why increment the count? Well, because you have to prevent other threads from deallocating and overwriting the code of f with some other data structure while we're busy running it, and the reference count is how Python remembers that someone's using it. So the OS offers cool optimization when processes need to share code, but reference-counted code objects just can't take advantage of this. Now, another basic concept, dynamic linking. Take another look at our Python process. The Python binary and the libc.so library started out here as separate files sitting on the disk, but Python needs to call some functions inside of libc to do its job. How does it find where those are? We will now take a trip back into the old days. In the old days, the very first C program fit into a single file. But then that first program got really big, and it took forever to compile. So they came up with a convention of writing small C language program files that would each get compiled into what was called an object file. That was the expensive step, and then they did a fairly quick step called linking to put them together into a program. So if you edited a C file, you only needed to recompile the source files you just edited to their .o equivalents. So how does the linker that does that last linking step connect, say, a module that calls a foo function with the separate module that defines it? The answer is that every .o file has a table of names that it defines, and also in that table, next to the letter U, are the names that it needs that it's going to rely on some other function, some other object file to define. There's a little utility on OS X and Linux machines called inim, short for names, that will print out for you the names provided by and the names needed by an object file. Now the linker just plays matchmaker between the names that are needed and provided among all of the .o files. Linking will then return an error if this matchmaking task fails and a name that one .o file needs just isn't found in any of the others. People, at this point in history, started to, now that they had this intermediate form, this .o file, well, they started sharing useful .o files with their friends at Bell Labs. And these quickly grew into collections. No problem, just like we have zip files and tar archives today, they actually had an archive tool back then in 1971. It was called AR, and so they would use the archive tool to bundle together a bunch of .o files into AR-produced .a files. Think of what that must have been like to live back when the single-letter extensions hadn't all been used up yet. You could invent the idea of an archive, and it was just .a. If you have an OS X or Linux machine, look on it. There are still those .a files with exactly the same structure sitting on them today. This is a command I ran a few days ago on my laptop here on a .a file that happened to be sitting in user lib, and look what's inside of the archive. .o files. Just like in 1972 or 3 when this practice started at Bell Labs. So the linker was given the power to search a .a archive, looking through the .o files and linking your programs with the ones that provided names that you needed. The .a file, full of .o files, came to be called a library. And there was now a problem with computers running out of memory, especially back then, that if everyone lets the linker copy, say, a popular function everyone started to use called printf.o into their program, then when many programs are running at once, they'll all be using up some memory by having their own copy of printf.o. So the solution was the invention of the modern .so shared object files that can be added to the page table of every program that needs them. The last-minute linking that takes place at runtime to connect Python to the shared object file is called dynamic linking and occurs at runtime when they find themselves sitting in RAM together. Now, oddly enough, the .so shared library is all you need to run a program. But guess what? You still need that old-fashioned archive of .o files to compile, and that's why you need to install on an Ubuntu box libxml2dev when all you want to do is compile the Python LXML module that uses a shared object that's already there. It's because compilation needs metadata that isn't in the stripped down memory efficient shared objects. It's only in that original set of .os. So anyway, you can see, if you're ever curious, the libraries that a program like Python needs with a command on your system called LDD. It will list them out. You can see the specific names it needs with nm, that same command. Though if you want to see what names it needs at runtime dynamically, you have to give the -d dynamic option. Now, not only is it usual for the Python binary to be dynamically linked, but Python extension modules sometimes link against shared libraries too. The LXML etree Python module is quite famous for this. Shared libraries cause some problems. They save RAM, but when a program chooses not to carry a static copy of every library it needs, there's the danger that a library it needs will be upgraded or removed out from under it. For an example, I'm going to show you the simplest possible small shared library together with a Python module that uses it so we can induce these errors and learn the error messages. I'm going to create a shared library, libtiny. There it is, GCC with -shared. We'll turn this into a shared library. And now I'm going to make a Python module that doesn't actually do anything, except that during it provides no functions or anything, but during its initialization it needs to call that helper function that returns 42. And here again is the command to produce tiny module that Python can import. Having created these 2.so files, we need to add the current directory, if you follow through this later, to the OS shared library search path. Here's the command if you want to experiment with this. And now, we're all set up and you can confirm it's working by running LDD on tiny module, and sure enough, in the list of things it needs is libtiny. If we run import tiny, it works just fine. Now, what if Python can find tiny module, but the OS, because of some upgrade, can't suddenly find its dependency? And this is the error. I do a remove on libtiny.so, and that familiar error message comes out, cannot open shared object file, no such file or directory. We can simulate an incompatible shared library by recompiling it, now giving the function the name different helper, and now the error is a bit different. It says, when we try to load tiny module, undefined symbol helper. Why? Because the tiny module needs the function helper, but because of an upgrade, libtiny now provides a different name. They don't match. The matchmaking fails, and dynamic linking doesn't take place successfully. Cannot open shared object and undefined symbol are possible because the OS is trying to link a binary to its dependencies at runtime. Now for another puzzle piece. This is fun. Demand paging. The OS, it doesn't actually load pages from disk, even ones you've asked for, until you try to read or write from them. Imagine a program that's just started running and the Python binary takes up 3 pages and libc 2. At first, it won't actually load those in. It will instead only load in the first page that needs to start running, as one function calls another function, calls another function. It will load in only the pages that get touched and just leave the other ones out of memory to save resources. Pages are loaded from disk lazily. Heap allocation works the same way. How many RAM pages do you think would be allocated if you asked for 3 more in this situation? And the answer is none. All the OS does is remind itself that it shouldn't cause a segmentation fault if you try touching page 5, 6, or 7 later, but that it should then live up to its promise to give you a readable and writable page. But they're not actually allocated until you try doing an operation on them. This then, to bring this to a practical point, is the difference between virt and res when you run top. Who here has ever run top? Several of you, good. You've seen these 2 columns? Virt, the virtual image, is all memory pages that promise not to return a segmentation fault, whether they've been allocated or not. It's res, the resident set size, that counts how many pages you've actually been allocated that can't now be used by other processes. So our sample little process here has a vert of 8 pages because you've asked to use the 5, 6, and 700s, but the res is only going to be the 4 pages that the OS has actually allocated for you. Thus, only res can really run you out of memory. Vert can be as big as you want because it doesn't actually consume pages of RAM. Look therefore at res when you wonder where all of your RAM is going. There's actually a cool file on Linux systems that lets you see how much of each physical RAM segment is populated with pages. Here are some segments of a new Python process sitting quietly at its prompt. You can see that in booting, Python only touched and paged in about half of the binary, and only about a third of libc needed to be used. And so to give you a small example, I'm going to call here frozen set, which just happens to be a function that Python doesn't use during its own boot process. And you can see that 20 new kilobytes had to be pulled in from the disk before that function could finish because the OS had saved memory by not actually reading them from disk when Python started. So invoking new sections of a binary or library pulls more pages into RAM. But since binary and library code can always be reloaded from disk even once it's there, the OS will often just discard those pages if things get kind of busy. Here's a little program that allocates a bunch of memory and makes the OS think this is a crisis and we're running out of memory. I ran it while leaving that other Python process sitting quietly at the prompt, and look what happens. Look at the RSS set from before I ran the big memory program to after. 452K, half of the image, was just deleted from memory because the OS knows if I ever try to touch that part of the binary, it can always pull it back in. And the Python process will never know. Those pages get reloaded, and this is where the name comes from, on demand from disk if you ever try to access them again. Well, there is one difference, of course. The process, if it needs those pages again, will slow down and pause as the disk head moves and those resources are reloaded. Always remember the wonderful blog entry by Gustavo Duarte, who pointed out that if the L1 cache is like taking 3 seconds to grab a piece of paper, then a hard drive seek is like leaving the building to roam the earth for 1 year and 3 months. But you know that. That's why your web browser takes so long to start the first time. And now, I'm going to teach you about a real Unix superpower that you just can't do anywhere else, forking. On primitive operating systems, the only way to create a new process is to start a whole new program from the beginning. If these are the steps the Python interpreter needs to get going, then if you want to start a separate Python process, you've got to send a second interpreter through those same steps. But Linux and OS X support fork. If they come to a fork, and the idea of fork is that you come to a fork in the road and take both forks, creating 2 processes that act as though they went through all of the same initialization code up to the moment of the fork, a child process that continues from the parent state. Now the OS could implement fork naively, because now the child has a life of its own and might make different decisions, by making a complete copy of all of the child's RAM. But immediately copying every page could take a long time for a large process, and during the copy, both parent and child process would be hung, waiting. Instead, as you might guess by now, the OS implements fork lazily instead, copying pages on demand only when the parent or child performs a write. So at the moment fork has happened and child and parent are running separately, everything will be marked read-only so that they're sharing the same pages between the 2 processes. Only as they start making writes to the pages they need to write to have different histories going forward does the OS pause them, make a copy of each page, and set them going again. How well does this usually work? It works great. Only the differences that develop between a parent and child memory image need to have memory allocated for them. But how does it work for Python? Terribly. Thanks to reference counts? merely glancing at data with CPython forces the OS to create a separate copy. Here I create a list. I'm about to do the same experiment with PyPy, so I throw a string in with all the integers so that it can't create an apples to oranges comparison by doing an integer list behind my back. The idea is we create a huge data structure, fork into two processes, and then I just ask parent and child to read that list, not changing it, just reading over it. In CPython, again, looking at that proc file on Linux, look at the shared dirty pages and the private dirty pages. You can see that at the moment of the fork, almost all of the heap in this process is shared between parent and child. After I simply read the list, the OS has had to copy, in this case, 100 megabytes of RAM to create an absolutely identical copy just so the reference counts can be fiddled separately. At the end, only 0.5% of my memory is shared. All the rest of that read-only data structure now exists twice. I tried the same experiment with PyPy 2.8. It used a little more memory. Here's what it looked like right after the fork, and here's what it looks like after the iteration. 96.1 of the heap remained shared, reading over a large list. The lesson is that a forked worker process in Unix, forked worker processes share memory if the parent process pre-builds a read-only data structure, but that this doesn't usually work very well in CPython. Finally, I should mention explicitly sharing memory. How can two Python procedures share writable memory deliberately if they want to collaborate? Everything we've talked about now simulates every process having its own memory image. Everything I've talked about delivers to the process what looks like memory that only it is writing. But what happens when you actually want several processes to see each other's writes and not have this protection and isolation? The first solution you might have used before is threads. Creating a thread is actually like fork, except that the heap remains shared between the threads of control. Python supports threads on both Unix and Windows, and though the stacks have to be different because each thread will make a different series of calls and have a different history, all of the lists and dictionaries and other writable data structures in your program remain shared because the rest of the page table is shared in common between the two threads. Since threads share every data structure, they have to be very careful. And that's different from memory maps. Using mmap, which I believe also works under both Windows and Unix, you can create shared memory that will be inherited by all the child workers that the parent forks. What happens here is, like normal processes, they each have their own domain that only they can see, except for that mmap segment. It's some pages of memory they can write data to and see each other's writes to support very fast RAM-based communication without requiring every single data structure on the heap to carry locks or other protection. One last really cool mmap capability. Remember how the OS loads pages from binaries like Python and libc only on demand? It doesn't read the whole thing in if it doesn't need to. Well, with mmap, you can do that yourself with normal files. If you give mmap an argument, the file number of a file you have open, then instead of an app where maybe you have to seek and read and write and seek again to move back and forth in a file, it simply makes the file look like an array of bytes in memory, and it pulls the file's pages in as you try to read from them and writes the changes back to disk as you touch them, but typically with only a small working set needed to be loaded at any given time. So there you have it. Your process is all-access memory, it turns out, through the mediation of a level of indirection called a page table. Page tables power all kinds of fun RAM optimizations that have been happening behind your back: demand loading, shared libraries, memory maps, the magic of fork, and threads. And keep in the back of your mind that because PyPy lacks reference counts, it lets the OS do its magic and conserve more resources. Thank you very much.
Thank you, Brandon. That was great. We have time for like one or maybe two quick questions. We'll see how we go.
I'm curious. I recently started using mmap in a non-Python context, and my free RAM meters, like free and top and everything, are behaving strangely. Do you know if mmapped RAM that's actually resident shows up in, does it affect free counts? Or does it somehow go behind its back?
That can change between versions of an operating system. Reporting tools can often have odd effects if the last time the guy touched the code, it was under a version of Linux or OS X that did things even slightly differently. So I would have to look at the particular readout you were seeing. What I would expect free to do is only show pages disappearing when they were allocated. And I think that when you mmap, you can actually ask for the pages to be sort of delivered when you ask for them, because some processes that memory map don't want to get a memory error later just by touching a page that it turns out didn't get allocated. And so I think mmap actually does tend to go grab all of the pages that will be needed so that it doesn't have to guiltily kill the guy later because it didn't actually have the RAM that he asked for. So I would expect it to, a gig of mmap to take up a gig of RAM, and if that's not what you're seeing, it would be curious to look at the tools in the OS and try to figure out if they were confused or doing some cool trick.
Thank you.
All right, that is indeed all we have time for, so thank you again, Brandon. And now stick around because we have
invoked every time your process hits main memory. Well, first, security. If the OS is careful and only maps into your memory area your own pages, then you won't be able to see secure data in other processes. You won't be able to see any secret operating system memory containing sensitive information if it doesn't map its own pages into your memory area. And before the OS gives you pages that have been previously used, it wipes them with zeros so that you cannot learn passwords or other data that were there. And obviously this provides stability. You can't very much corrupt another process's memory or the operating system and cause a crash if you are not permitted to write to its blocks, because they're simply not even visible. They don't even exist to you because they're not in your page table. Now, let's add another dimension of complexity to this picture, the idea of protection. Real page tables include separate read and write bits. In general, the rule is this, that you can write to your own stack and heap as much as you want to, putting new data there, but you're only allowed to read executables and religious wars. You say, run my editor, and the OS loads it into memory along with any libraries that it might require, taking up a few pages of memory. The editor's main function now gets kicked off and starts calling other functions, so the OS will automatically start to allocate stack pages as that call graph grows. That tends to start at the top of memory and work down as more pages are allocated. Notice the fairly random numbers. They can be pulled from anywhere in RAM that there are free pages because the association is a completely free one. Now, your editor might then, as it starts up, need space for data structures, lists, dictionaries, buffers. It says, I need more memory. The OS says, okay, have some. And you get another growing memory area called the heap, which instead of holding variables that go away when a function call returns, it holds persistent data structures. Again, for those of you new to Python, things like lists and dictionaries. So, what are the benefits of this entire level of indirection that has to be implemented in hardware and in
5 minutes dedicated to questions. Please welcome Brandon.
Welcome. Congratulations for slugging it out and making it all the way to the very last talk slot at PyCon. Let's get started. Imagine, if you will, a computer with 1,000 bytes of accessible RAM, numbered 0 through 999, each storing a byte. We can split this memory into pages by grouping together addresses that share a common prefix. If, for example, we want a page size of 100 bytes, so our 1,000 bytes of main memory are 10 pages, then page 3 would include all of the addresses that begin with the number 3, 300 through 399. Now, what is a page table? It sits in between the part of the CPU that runs your code and the RAM on your machine, and it rewrites the leading digits of every processor memory access before the RAM chip gets to see it. Here's an example. The addresses that your process asks for are called virtual, and the actual addresses delivered to RAM are called physical. So this example page table, remember, only looks at the leading digits. Your process attempts to read byte 821. The RAM chip actually sees a request for 6321. Process tries to read byte 190. Instead, the RAM chip would see a request for 3690. A write to byte 522 would be mapped into a write to real byte 6022. And for pages that don't have an allocation at all, an event is generated called a page fault, which pauses your program, returns control to the operating system, and as we will see, the OS then has several options about how to respond. So what kinds of things get stored in the bytes of these memory pages? Well, everything your program needs. The executable code itself, the stack of function calls that are currently underway, the heap with all of your data structures, lists, and dictionaries. These resources, they tend to load gradually as your program runs. Imagine running your editor, which I will not name to avoid obvious library. So the example app we were looking at would have write bits set on the stack and heap, but only let you read from the editor binary and the libraries that it used. If you illegally read or write, then the OS, again, gets signaled, but this time, instead of responding to your page fault by giving you more free memory, the OS will stop you dead with what's called a segmentation fault, which basically means a page fault that made the OS angry. So here, a read from 331, per the rules we saw earlier, generates a segmentation fault because there's no page there. But we've now also learned that you can't write to certain addresses, even if they're mapped, if they're marked read-only. Now, read-only pages, this invention, gives the operating system a new superpower: sharing. Read-only binaries and libraries, when those pages are protected, that means the OS can reuse those pages in everyone's page map and securely share those binaries among several processes. Here are two different processes doing two different things that